go ahead and let's take a general look at acids and bases and review some of the ideas that were covered in first year chemistry. So the nature of acids and bases. So acids and bases that are encountered in our everyday lives includes things that are found in our foods, things that are found in our cleaning and cooking products, and even things that we see and utilize in medications. Okay, so some acids of note. So citric acid is found in both oranges and lemons. Vinegar is also an acid. Acetic acid is what we experience when we're actually consuming vinegar in our chips or whenever we put it in our salad dressings and things of that sort. Some bases that we encounter include baking soda. Okay, and we all have seen a container of baking soda at some point in time. Okay, antacid tablets, so things we utilize to calm down our upset stomachs are examples of bases. And last but not least, ammonia. Remember that's NH3. Is also a base that we may have, just in our cabinets or sitting around in our everyday household products. So acids and bases were also probably covered a little bit more in depth in your first year chemistry course. Acids may have been described as being sour, hence the effects of the lemon when you take a bite of something really, really sour. Litmus paper turning to red, so the blue to red transition from litmus paper is another example of a way that you may have described acids. Bases, on the other hand, described as bitter and slippery to the touch, and they cause the exact opposite effect. They cause the red litmus paper to turn blue. These might have been ways that you guys kind of covered to describe or differentiate acids and bases. Another way you may have discussed acids and bases is with respect to the Arrhenius concept. So basically, when you put an Arrhenius acid in water, the concentration of H plus ion is going to increase. And in the case of an Arrhenius base, when you put an Arrhenius base into solution, your OH minus concentration or your hydroxide ion concentration is going to increase. So these may have been ways that you discussed the descriptions of acids and bases in a kind of basic way the first time you looked through chemistry. So we're going to continue utilizing some of these ideas and of course expanding on them. So another definition that you may have encountered while learning about acids and bases basically refers to the Brönsted-Lowry definition of acids and bases, and in those situations you have acids referring to proton donors and bases referring to proton acceptors. Okay, please understand that when I'm referring to proton donors, I'm not referring to the subatomic particle. I'm referring to that H plus ion. Okay, so guys, remember the H plus ion is formed when the electron that the hydrogen has is given up, and you form this positively charged ion that you see here. Okay, so Brönsted-Lowry definition, acids are going to donate protons, bases are going to accept them. So in the case of an acid and base reaction, that's really just, in the case of Brönsted-Lowry, a proton transfer. Okay, so basically in order to be an acid, you must be in the possession or must own a proton that can be transferred. So in this case we have HCl, which is hydrochloric acid, and it in fact can transfer a proton in the form of its H that's right here. So if we have this Brönsted-Lowry acid, we need to have a base. In this case, H2O is the acceptor of that proton. So what's going to happen is this H in the HCl is going to get transferred to the H2O. So we're going to end up with a Cl minus all by itself, so a chloride ion. And when this base picks up the proton, you're going to get H3O plus, or that hydronium ion. So basically, you start with an acid and a base. One is a proton donor, one is an acceptor, okay, and you end up with what's known as a conjugate base and a conjugate acid. So notice that the conjugate base, okay, is being produced from the original acid, and the conjugate acid is being produced from the original base. Okay, so basically being able to identify all the components, i.e. which one's an acid, which one's a base, and the subsequent conjugate base and acid pair that's going to be produced is going to be necessary. So let's look at the conjugate acid-base pair a little bit more closely. Okay, so a conjugate acid-base pair is a pair of molecules or ions that are related to one another by the gain or loss of proton. Okay, so basically Brönsted-Lowry processes, or Brönsted-Lowry acid-base reactions, are going to give you conjugate acids and bases. Alright, so that conjugate acid, as I said, is going to be formed when the base itself accepts a proton. So in the last example we looked at, remember that H2O was the base. It accepts the proton and produces the conjugate acid. Okay, in this case a hydronium ion. Okay, the conjugate base is the substance that's formed when an acid donates a proton. So whatever we have left over after this acid gives up this proton right here, that's going to be our conjugate base, and in this case a chloride ion. Now there are substances that can act as either an acid or a base, and those are called amphiprotic species. And in that case, basically they can either accept or give up protons. And I guess one of the most famous examples, or the examples we'll encounter quite a bit in this class, is water. Water is in fact amphiprotic. Depending on the situation, it can either behave as an acid or a base. So in this case, we have hydrochloric acid, we have H2O, so the HCl is a stronger acid than H2O could be, so HCl is going to transfer its proton to H2O and give you your conjugate base and conjugate acid respectively. In this case here, NH3 is actually a relatively weak base, but that makes the H2O molecule, in this case, the stronger acid. So in this case, it will transfer its H plus ion, or its proton, to the NH3 and produce our hydroxide and our ammonium ion conjugate base and conjugate acids. Okay, so as you can see, depending on the situation, water is going to either behave as a base or an acid or exhibit these amphiprotic features. So just as a quick refresh or a little bit of emphasis, this H3O plus, or the hydronium ion, as written here, is really just a water molecule that's actually picked up that additional proton. Okay, so when you have water, right, okay, it's going to be hanging out in the container, and basically what's going to happen is it's going to pick up this proton that's floating into solution and subsequently give you this hydronium ion. Okay, and that hydronium ion basically makes it where that H plus ion that's coming from your acid is not basically floating alone on its floating alone in solution. Whenever you have an acid that's been put into water, there is going to be hydronium ions present. However, guys, a lot of times we will kind of interchange the hydronium ion and the proton as meaning the same thing. You can see that in some log calculations when we get to the pH. But just be aware that the reality of it is that H3O plus is always going to be present in these acid-base situations if water is present. So let's go ahead and let's look at some specific examples of acid and base pairs. We need to become proficient at identifying them as well as predicting them. So if I'm utilizing the acid and base definition associated with Brönsted-Lowry, and I'm looking at the transfer of protons, and I'm given two species here. Okay, I'm giving NH3 and I'm been given H2O. Okay, if I know that this is going to be an acid-base reaction, I basically need to utilize the thought process of what is going to give up protons. Okay, so who's going to donate protons? Okay, and who's going to receive protons? Alright, so whoever's going to give up protons is going to be my acid. Okay, and whoever's going to accept is going to be my base. Alright, so in the case of NH3, we know that NH3 is a weak base, or at least that's something that you guys should memorize. And we know that H2O is amphoteric, so it can go either way. It can either behave as an acid or a base. So in this case, we know that NH3 is a weak base, so therefore H2O is going to act as an acid. Acids give up protons, so we know that this acid is going to give up its proton to this NH3. Okay, so you're going to end up with a NH4 plus ion because the NH3 is going to pick up that proton, and you're going to end up with a hydroxide ion after this H2O molecule gives up one of its hydrogens. Okay, and as we discussed, your conjugate acid and your conjugate base are produced from the original bases and acids. So your conjugate acid is going to be from your original base, right? So your conjugate base is going to be from your original acid. Now another way to look at these is if you look at these all by themselves, okay, you can kind of look at, hey, who's going to behave as an acid or a base? Okay, well, NH4 plus has 4 protons attached to it, or 4 hydrogens attached to it, while the OH minus over here only has 1. Okay, and so I guess from that, you could probably deduce from that, okay, that your NH4 plus is more likely to be an acid, and your OH minus is more likely to be a base. That's a little less straightforward than just looking at the original source acids and bases. So remember, H2O is amphiprotic. It could be either an acid or a base. Okay, and NH3 is a weak base. You must memorize this, so please write this in your notes and please take time to log it to memory. Okay, so if we go ahead and look at this next example, we have acetic acid. Okay, we have acetic acid and we have ammonia again, right? Okay, so in this case, guys, knowing these molecules, okay, how am I going to know that this is acetic acid? Well, the reality of it is, guys, is this is connected to your polyatomics, okay, CH3, COO minus. This is one of the 85 ions you're supposed to know, okay, so this is acetate, okay, and in the case of adding that H, that's right here, this actually becomes acetic acid. Okay, and we just talked about NH3 being a weak base. You must memorize this. This is ammonia, guys. Just know it. Okay, so we have this acid and base combo that's seen here. We know that our acid is going to transfer our proton over to our base, okay, to produce our conjugate base and our conjugate acid. Notice, acetate is what we've produced here, and our ammonium ion are both produced. Now, our conjugate base obviously is sourced from our acid, right? Okay, it makes sense that acetic acid is going to give us acetate ion. So in this case, we got our conjugate base. Our base here, our original base is NH3, so bases accept protons, so that gives us our conjugate acid, which is that ammonium ion. Now, this will come into effect later, but something that you guys need to be aware of, or at least be cognizant of, is that your conjugate base and your original base, depending on their presence, okay, may actually compete for the H plus ion that's produced from the acid that's added to the solution. Okay, so just be aware that later on, especially when we talk about weak acids, we're going to be looking at the conjugate bases and basically how they can affect the consumption or the using of H plus ions that are put into solution. So that won't be important now, but please be aware that, you know, the bases that are produced, or even the acids that are produced as our conjugates, still potentially have the option of affecting H plus ion concentrations in the solutions. Okay, so let's go ahead and let's look at some situations in which we need to identify our conjugate base or our conjugate acid for Brönsted-Lowry acids and bases. Okay, so in this case, HCl. Okay, if I have HCl, if I put it into water, right, this is going to behave, this HCl is going to behave as an acid. So all of these are examples of acids in solutions, right? They all have that H plus ion that they can donate. So if chlorine donates its H plus to the base, okay, so whatever that base may be, all right, it's going to produce Cl minus as its conjugate base, all right? Okay, if HSO4 minus donates its proton, okay, it's going to produce SO4 2 minus as its conjugate base, right? And if NH4 plus ion is our acid, okay, it's going to produce NH3 as our conjugate base. Notice all of these have one less proton. Okay, obviously that means that they could pick up an extra proton. So these are all examples of our conjugate bases. You guys need to be able to identify what it is that's going to be produced. So, the way I'm thinking about this is, okay, what am I producing when I put that acid in with, say, water, right? Okay, so in this case, H3O plus and Cl minus for that first example. Notice the Cl minus is my conjugate base because it's produced from my acid. Okay, if we look at our Brönsted-Lowry bases here, okay, so basically we know that they're going to be picking up protons. Okay, our carbonated ion is going to become HCO3. Okay, our acetate ion here is going to become acetic acid. Okay, and our NH3 here, therefore, is going to become NH4 plus, our ammonium ion. Okay, so notice how these have all gained one proton and become conjugate acids of the Brönsted-Lowry bases that are shown here. Okay, same thought process, same approach, and the identifiers, or the ability to identify each of these, is going to be important. So make sure that you practice and get used to what's being transferred, who's accepting, who's giving.